In this video, I'd like to talk about the math question of the day for April 8th, 2023. And in this problem, we need to determine if the given function is continuous or discontinuous at the indicated points. So we have this function f of x, which is a rational function, a ratio of two polynomials, and we need to look at these three specific x values. So to answer a question like this, you do need to have an understanding of calculus and in particular limits and continuity. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through it. And since we're talking about continuity, we will need a definition for what a continuous function actually means. And of course, if you do have suggestions for future questions of the day, feel free to leave those as comments. So let me first paste in a definition. And with this definition, we can say that a function is continuous at a specific point if the limit as x approaches that a value is equal to the function evaluated at that a value. And a function is continuous on an interval if it's continuous at each point in the interval. And this definition might be a little bit confusing. So let's look at a few different examples. Let me draw a quick coordinate plane here. And let's say we have some function, which we can call, let's say g of x. Let's say it looks something like that and ends there and then starts up down here. And maybe we'll have another gap, something like that, and maybe even a hole in the function there. So this function we can call g of x. And when dealing with continuity, it does have a fairly intuitive approach. Continuous functions do not have holes or jumps like this. So we can see, just visually speaking, that here the function is not continuous, as well as right here and at this hole. But to formally understand it, we're saying that the limit as x approaches some specific a value in our function, we'll use g of x here, this is equal to the function actually evaluated at that point. And let's say we're looking at this specific value here. We can call this an x value of c. Let me actually just use a different color there. So if we look at c, we can see that the limit when approaching c from the left-hand side is not equal to the limit as x approaches c from the right-hand side. And for this statement here, this limit to actually exist, we can clarify that as x approaches that value from the right in the function, this has to equal the limit as x approaches that value from the left, again, in that specific function. So for this limit to exist, the limit from the left and the right have to approach the same value. And we can see right here that they were approaching very different y values, which is why this limit does not exist there. And it would be the same for this right here. That's the reason why this wouldn't be continuous. The limit from the left-hand side is not equal to the limit as x approaches from the right-hand side. And looking at this final hole right here, we can see that as we approach, let's say this is d, as we approach d from the left and as we approach d from the right, they do actually equal the same y value. So in this case, the limit does exist and it's equal to whatever this y value is. However, the function does not exist there. So it's the right-hand side of this equation here that isn't working for us. If we plug in our value of d, we can see that it's not defined here. There is no y value assigned to an x value of d. So in this case, the limit does exist and it does equal whatever this y value is. However, the function is not defined there. So it is not continuous here. But if we look at, let's say, this point right here, we can use an x value of b, and let's say its y value is g of b. the function does exist at this point and evaluates to some specific y value. And as the function approaches b from the left-hand side, this is equal to the same y value as the function approaches b from the right-hand side. So in this case, at this point, and really any point along this interval here, it is continuous because the limit exists, and if we approach it from the left or the right, it's equal to the same value, and the function is actually defined there. So continuity might look obvious and intuitive in many cases, but it does have a very formal definition. So to answer this question, we need to see if the function exists at each of these 3 points, and if the limit from the left and the right actually approach the same value. So let's make a little bit of room, and we can go through this carefully. We can start by just looking at whether or not the function exists at each of these 3 points. So we can start with a, when x is equal to -1. If we plug our value of x into the function, we get 4 times -1, which is -4, plus 5. And we have 9 minus 3 multiplied by -1. We get 1 up top, and down below we have 9 plus 3, which is 12. So the function exists at this point. And if we look at b, we can plug in x is equal to 0. And when we do so, we get 4 times 0, which is 0, plus 5. And in the denominator, we get 9 minus 0, which is 9. So at x equals 0, the function does exist. It is defined there, and it's equal to 5/9. But if we look at our final point, c, when x is equal to 3, here we run into a problem, since when we plug in 3, we get 4 times 3, which is 12, plus 5 in our numerator, which will simplify to 17. But in our denominator, we have 9 minus 3 times 3, or 9 minus 9, which is 0. And since we end up with 0 in our denominator, we know that this is undefined, since we cannot divide by 0. There is no defined answer for that. So at this x value of 3, the function's not defined, so we can eliminate this as a possibility for continuous points. We can say that when x is equal to 3, the function is not continuous. And we can actually look at the limit from the left and the right and see what happens to the function and show that the limit doesn't exist there either, since the x values will approach completely different y values whether we approach it from the left or the right-hand side. So let's focus on a and b. We know that the function exists there, but let's consider the limits. And let me start by making a little bit of room, and we can rewrite this problem down below. We can just paste that in. So for our 2 remaining points, we do need to be careful with evaluating the limit. So let's say for a, we want to look at the limit as x approaches -1. We could just plug it in like we normally would evaluate a limit, but really we would need to be a little bit more careful. We need to use the properties of limits. So let me first write in what we have. We have 4x plus 5 over 9 minus 3x. When using limit properties, this would be equal to the limit as x approaches -1 of our expression in the numerator divided by the limit as x approaches -1 of our expression in the denominator. And when we have a sum, we can take the limit of each term. So we have x approaching -1 of 4x plus the limit as x approaches -1 of 5. And this is a bit tedious, but this will essentially break down the properties of limits. And it works the same way when we have a difference. We can split each term here and take the limit as x approaches -1 of 9, and then subtract the limit as x approaches -1 of 3x. And we can go one step further when we have a product, or I should say when we're multiplying by a constant, when we're multiplying our variable by a constant, we can essentially factor that constant out, where we have 4 multiplied by the limit as x approaches -1 of x, and the limit of a constant is just equal to that constant. Since there is no variable here, this is just 5. And in the denominator, we have the same scenario here as we did up here. When x approaches -1 and there is no x value, this limit is always equal to 9. And we're subtracting the limit of a product where our variable is multiplied by a constant, so we can factor that constant or that coefficient out so that we have 3 times the limit as x approaches -1 of x. And at this point, since we've isolated our variable, now we can actually just plug it in. We have 4 multiplied by -1 plus 5, and we're dividing by 9 minus 3 multiplied by -1 if we just plug it in here for x. And we've seen that this numerator will simplify to 1, and our denominator will simplify to 12, which you might remember is the exact same fraction that we got when we just plugged it in. And all of this should make sense. This might seem a little bit tedious, but this is just applying the basic properties of limits. And as an exercise, I encourage you to apply these same properties when plugging in x equals 0. But if you do all of this work, you will find that the limit as x approaches 0 is also 5/9, which is what happens when you just plug in 0 for the function. So in both cases for a and b, this condition is met, and therefore the function is actually continuous at both of those values.